You can hear me well, and so it's a pleasure to welcome you all to the second Quid Ultra colloquium here at the Department of Physics, and to have finally a speaker in person despite a difficult situation. It's a pleasure also to welcome Silvia Celli, who has been a PhD student of Felix, and so she has proposed to introduce him, and I think it's a very good idea. So I leave the floor to you, Silvia.
So thank you very much, Raffaella, for the invitation. It's a pleasure to introduce you, Felix Aharonian, which is a professor at the Dublin Institute for Advanced Studies, and it is an external member of the Max Planck Institute of Nuclear Physics in Heidelberg. So Felix is has more than 40 years of research. He is an expert in both experimental and phenomenological high energy astrophysics. He has been honored in 2010 of the Bruno Rossi Prize of the American Astronomical Societies. This is one of the major achievements in the field of high energy astrophysics. So his main interests are about radiation processes and propagation of high energy particles in the universe. He studied many different kinds of sources, so pulsar, gamma ray burst, and relativistic outflows. He has been one of the pioneers of the imaging atmospheric Cherenkov telescope technique, in particular the stereoscopic mode of these instruments, and has been working and starting basically both the IGRA experiments and the DS experiments. So today he is mainly involved in the Hess and LASO collaborations, and his seminar from today is about PeVatrons and the Century-Old-Mistery of the Galactic cosmic rays. So please, Felix.
Thanks. Can I move this mask, or?
Yes, you can.
Just when.
Okay.
So
and this works.
From large distance, that's fine. Thanks. Okay, I'm very happy to be here, and it's one of the first, real seminars. So it was so we returned to real life now, and so I should say that I'm very happy to, of course, and I appreciate the invitation to give a talk here. I remember I gave a talk. I don't remember, maybe Tonino invited me actually in 2007 or 2006. I don't remember, that we just started this experiment, and it probably was in this, even in this the same hall, and so that was a very exciting times. Then when TV astronomy started, and it would not be exaggeration to say that was a bit revolution. In fact, TV astronomy, we witnessed that, and it looks like we are now witnessing the second revolution, now PV energies, and that has a direct relation to my talk. And because the particles emitted with energy more than 100 TeV apparently are produced by gamma rays above 100 TeV are produced by particles with energy more than 1 PeV. So it has many implications. One of them, of course, these are cosmic rays. And in that sense, I want to relate to talk is not just only that just simply origin of the cosmic rays, but one specific aspect of that, the particles which produce the factories of cosmic rays contributing to local cosmic rays around 1 PeV. So, and that now I think we are close to breakthrough to understand the origin of these accelerators. And in fact, it will be also have impact on the general topic of the origin of the cosmic rays. So you can see this kind of statement about the origin of the cosmic rays, that it remains, original cosmic rays remains a mystery. It is a standard statement since decades, but still we make this statement. We could find this in the very recent reviews, and I would say that is a bit why so pessimistic, this statement? Because to the last extent, the researchers, cosmic rays physicists are disappointed that still we don't know which sources contribute to the cosmic rays. So that is a bit, it is true, we don't know, but it's even not clear we will know at all in future. What I mean, we could recognize sources that contribute, but exactly which one contributed the local cosmic ray flux probably will be not so easy, but maybe it's not as a fundamental at all. So in that sense, I think I'm going to talk about that, but in that sense, I think it's a bit exaggeration when we call the mystery. So we know a lot of the cosmic rays, in particular from galactic cosmic rays. So, but of course there are challenges. We face challenges, and one of them is explanation of 10 to 15 eV protons. It's not just number. Just to say what is the specific in this topic, when we call PeVatrons, it's very popular now. I mean, just as a PeVatron sounds very nice, but the problem is very simple. It's very difficult to accelerate particles in galactic type sources. No problem to get them in extragalactic sources, not problem at all. But in our galaxy it's difficult. So that is the basic problem. So you need very special accelerators, extremely effective accelerators to get to 15 in our galaxy. One may ask, okay, why do you suffer so much? Why don't like to have galactic, the 10 to 15 eV particles extragalactic? That is also is not discussed much. In fact, this is it's very difficult because these particles have energies are so low. I mean, in that case, low because compared to the extragalactic scales. So propagation, even you assume very fast propagation. I mean, diffusion coefficient large. Hubble time will not sufficient to get these particles for real extragalactic distances. So it cannot be doubt that 10 to 15 eV particles are galactic, because typically people use think, okay, they are isotropy, but isotropy is not a big deal. I mean, here is most important if you say why they have to be galactic. This is because even Hubble time was not sufficient to get them. So this is one of the points. Now, so what do we know about cosmic rays? So as I said, below knee, there's a feature. You can see that feature. Oh, sorry. Here, a specific feature is just a few PeV. Actually, don't know these are protons or nuclei. In nuclei, it is a PeV per nucleon, so it's a big difference, by the way. So we are trying to explain that part. Typically, we say this is very nice, Paolo spectrum going from GV to even 10 to 20, but it's not real. If you go closer to narrow energy band, you could see structures, and here you see two structures, the knee and the ankle. But if you go even deeper, then you'll see, I'll show that even more structures. So 10 to 15 galactic, more than 10 to 18 extragalactic. Is also a little doubt about that because anisotropy related problems. We don't know exactly what is between 10 to 16, 10 to 18. So from point of view acceleration, 10 to 16, 10 to 18 is not a problem by extragalactic sources. So maybe the clusters of nearby clusters of galaxies. So Virgo cluster, for example, which is just at 20 megaparsecs, or radio galaxy Centaurus A, or starburst galaxies M82, NGC 253. So maybe they are contributing. So we could not exclude that, certainly. But The consensus is that these particles are galactic. I mean, consensus may be not a good word, but somehow most of cosmic ray physicists believe this should be galactic. But then you could ask, okay, if they are galactic, if you don't know how to accelerate particles to 1 PeV, then how you accelerate them to 10 to 18? That would be really very, very difficult to do. So this question is, as I said, is relatively easy, this part, but it is maybe the biggest challenge, in fact. So I call them super PeVatrons. So that will be, I'll come to that point a bit later. So, okay, what I said more or less written here. Now I mentioned that there are structures, so we believe that there are smooth spectra, but there are a lot of achievements over the last maybe 10 years or less. We see very, very interesting structures in cosmic ray spectrum. So if the recent one, IMS found some hardening above 100 GeV, and then should come again steepening. These are other experiments, and again hardening. That is not clear, but maybe above 100 TeV. So in any case, we could ask. So if you suffer so much to accelerate them, do you need PeVatrons at all? So because you could say, okay, that is, you could see the spectra here. This is very nice, actually, the figure composed by Lipri and Garnetto. So one option could be this one. Another option could be that one. Just from the cosmic ray data, you could not distinguish, at least at this stage, you could not distinguish which works, because there's a problem of the mass composition. So depending whether the contribution of heavy nuclei, so there could be, the both are possible. So we would say we need future experiments. So by the way, the Lhasa most likely will be the best one, in at least in the foreseeable future. And Lhasa probably will tell us a lot about this near region just from cosmic ray studies. But what is interesting here, maybe again, hope will be connected more to diffuse gamma ray background rather than direct measurements. Well, maybe it's not right to say rather than, maybe both are important. But for gamma rays, is a big difference. The first one, and say this option, there are two extreme options, or this option. So if you measure gamma ray diffuse background, you could get a real the answer to these questions. Now, I want to say something which is, I mean, not everyone agrees with me, but nevertheless, I call it the fog. What we measure, local cosmic rays, it is a fog. There's nothing negative with that. But I think we should not exaggerate the origin of the cosmic rays, reducing to question which particles contribute to that fog. It could be different ways. It maybe, as I said, it will be very difficult to know real contribution, but in fact, this will be, it's not a very fundamental question. What is the more fundamental? These cosmic rays. I mean, it could be sources far from us, which do not contribute to local fog, but these are producers of relativistic particles. We call them, historically, we call them cosmic rays, but I mean, these are relativistic plasma. I mean, so it is a fog substance, in fact. So we have a radiation matter, radiation, and the magnetic field. So this is the visible universe. I'm talking about visible universe, not that matter. And this is a fog substance. And it's not just, and this substance you produce every day, every second now. In the universe, in different places, you produce, accelerate these particles. There are special machines, simply accelerators, which accelerate these particles, convert the available energy. It could be thermal energy, it could be like rotational energy pulsars, thermal energy of the, or kinetic energy of the explosion of the supernovae, and they convert this to particles, relativistic particles. So this is a real substance. This is a new type of substance, and they also play a lot of role. By the way, is just for dynamics of our galaxy. For example, very low energies, they are most likely the most important, the part which produce ionization, and without ionization, you'll not have star formation. So they could have a very interesting implications, but they're low energies. And but another interesting thing is here just the efficiency you accelerate this particle. This is incredible efficiency. You see now in two aspects. One, you should efficiency you convert the available energy to particles. It could go up to 50%, like in pulsars. So you convert the energy of the rotation of the pulsar. At the end, 50% goes to 50 particles. So this is really incredible, I mean, efficiency. But second part of efficiency is acceleration of the particles that, as individual particles. So acceleration rate, when you get 1 PeV or 10 to 20 eV. And that is also, you'll see now, it is going at the edge of reality sometimes. Just you need the best theoretical parameters, not fine tuning. Just you have to assume the best parameters to get these acceleration rates. So from this point of view, it is really, my opinion is even more fundamental than just to know which particles are contributing this local fog. After all, imagine if you tomorrow will have some supernova explosion next to us, cosmic ray density could be completely different, and we will see only that supernova results. So it's important. It's not so easy to at the end to recognize, but it's not as fundamental as to understand the physics and astrophysics of these objects. Now, how you do that? I mean, with cosmic rays, it's not so easy because particles, charged particles moving in magnetic fields, they lose the information about the points when they have been produced. So you need neutral particles, and these are photons, and especially gamma rays. Of course, they are also radio. It's very important, but about low energy electrons. Synchrotron emission in optical band, in X-rays, but gamma rays are, how to say, the best ones, I mean, direct ones, because they're very close energy of gamma rays to the energy of the parallel particles. Neutrinos, extremely important, has advantages and disadvantages compared to gamma rays, because advantages very clear. You detect neutrino, you know the origin of these parent particles. We have always confusion with photons. Always are hoping with increasing energy, going higher, then we'll have no problem. We say these are hadronic or leptonic, so high stage hadronic, but it's not the case. So now we are getting energies more than 100 TeV, still they are not clear. These are protons or electrons. So confusion is already there. So neutrinos, from that point of view, would be best. On the other hand, neutrinos only hadronic process. The physics is rich with gamma rays because they give you also information about leptonic part. On the other hand, neutrinos don't suffer absorption, so that is a positive part. Gamma rays do absorb, so you have to always correct the initial. On the other hand, because the cross sections of neutrinos much smaller, but for the same reason, neutrino is difficult to detect. So even having huge facilities, you have limited detection areas. Okay, and then it's coming the new players in this game, these gravitational waves. It's not directly, they are not related to, you don't produce the gravitational wave particles, but gravitational waves could play very interesting way. They could be connected to these accelerators. And so just to go, because I'm talking more about gamma rays, because today we have most information comes from gamma rays. And I said there was a revolution in this area. So we have a low energy gamma rays, MEV, GeV, which is the so-called domain of space-based astronomy. So you do with satellites, and PeV, and now very recently, since last one year, 1.5 years, also in PeV band. And PeV I called more than, okay, there's a mistake, I'm sorry, 0.100 PeV, not PeV, last line, but we called 0.1 PeV. It's already, you could say PeV astronomy, but now we see gamma rays direct exactly PeV of PeV energies. So that was absolutely unexpected. So now you see window is opened in a huge energy band, about covering 10 decades. And as I said, there was a revolution, this area at TV. Well, because also revolution was a GV, it was a Fermi. And then we have a second revolution in TV. And now we are witnessing a new revolution at PV. So it's really very, very promising, very nice area to work. So, so as I said, the revolution is good, but there's something more than just simple achievements. It was a big surprise to see so many TV gamma ray sources. It was really a big surprise. So hundreds of sources. But even more exciting is not just one type or two types or three types, more than 15 types of source populations. So this acceleration of TV engines is realized in a very unique way, independent what is the scales, what is the type of the object, could be neutron star, could be black hole, but always you see effective to TV. Okay, we start to become familiar with this, even strange. But what is even more, now we start to detect PV particles, or well, ultra-energy gamma rays, 0.1 PV and more. And as again, revolution, because we didn't expect that we see so many of them. But real surprise is how it could come. I mean, there's so many of PeVatrons. So that is a really big surprise, because I mean, you'll see how it's difficult to accelerate them. As I said, it's not just emotional wording saying just the incredible efficiency is really incredible, but there are many of them. So that is the some very exciting part of this. Now I just show this gallery. I think there are many talks showing beautiful pictures. This is not the purpose of not that. This gallery implies all sources which emit gamma rays. So that is really exciting. As I said, this is a very, I mean, personally, I'm not so much excited with the numbers, 100 or 1,000 or million, but different type of sources, and always you realize this effective acceleration. So you could see the stars, just the second one, Novi, by the way, was recently discovered, supernova remnants, microquasars, neutron stars, and coming the extragalactic object, which is not topic of this talk. But just to mention, just take only neutron stars. How many realizations could be neutron stars? So the pulsars, magnetosphere of the star. So we know they are just emitting gamma rays. Big surprise was here. Now we see also pulse emission of TV, which no one expected, but we see pulse emission also TV. So this is once, let's say, most common one, magnetosphere. Then you go to the pulsar nebula. So there are many. These are largest by the population. And this going to TV, and now we know they are going to TV. I'll come to that. I would not like to go on. We have binary pulsars. We don't know exactly binary neutron star mergers. It is related to gravitational wave, by the way. But there was a magic just reported. It was not at the level of statistical significance about that short GRB detection with magic. So what means short GRBs are connected with neutron star mergers. And then one of them was detected in gravitational wave. So that when I was saying that there is a multi messengers of the gravitational waves, I mentioned in this aspect. So you have the source, which is the origin of all the story. And you see, this is you have at least 5 type of objects producing accelerating particles, not simply accelerating to such high energies. So this is a real excitement. And I would just stop at that. So it's exciting. But what is another nice thing in this area? These are very high quality of experiments. I mean, this is you can do it. These are from Cherenkov telescopes, which is the great success over the last 20 years.
And now field is not saturated, it's still going on. And next will be CTA. So it's very optimistic what will happen the next. Maybe you don't know what will happen but you know that sensitivity will be much better. So that is actually sufficient. But maybe it's more important than many theoretical predictions, because whatever you do, something will come new, which you could not even predict. So this is a very nice, very, very nice future, very predictable. So predictable that there will be a bright future, but what will come, we don't know. Certainly it will be very exciting. But now I thought about further revolution. This appeared suddenly. So not for everyone, maybe for me, but not for some people sitting here like Pino. And so that was really, it was there quite modest. I mean, conferences showing this kind of figures. I personally was very disturbed and a bit even unhappy to see this sensitivity, such a good sensitivity. But that now is the case. So it is proved. You see the sensitivity is extremely around 100 TeV. It's very impressive, because if astronomers could be impressed, by the way, because having sensitivity 10⁻14 ergs per centimeter per second, it is a lot. And by the way, the angular resolution is large. For extended sources, is 0.2 degree. Of course, Chandra is extremely sensitive instrument, 10⁻16. Hubble is very sensitive, 10⁻17, but it comes from the angular resolution, arcsecond and better. If you go extended sources, you see that sensitivity is even better here, and you miss even more powerful X-ray instruments. Sometimes it disturbs X-ray astronomers, saying how could be just we are not sensitive, just for specific objects having large field of view. And another unique thing is this instrument, is this. So what they did, it was very ambitious to have square kilometer array. There are many detectors. I'm not going to talk about that. There's not much time, but it was very big. But second one, there are two types of detectors: surface, which provide 1 square kilometer, muon detectors, which provide rejection of hadronic showers. And it appeared that was so impressive rejection that the strong sources, like the crab, I'll show, you detect almost background free. The background is at least 10 times less than. So that is unique in astrophysics, by the way. Really unique situation. You detect signal without background, almost without background. So that is, so you reject with rejection such powerful and size, plus you have very good angular resolution, energy resolution, 15–20%, which is perfectly fine for spectrometry. If you have statistics. Now you could ask, what about statistics? So for the crowd, for example, you will detect 10,000 events for a few years above 30 TeV. So you have a background free, you have so many events, you have a angular energy resolution 15%. Of course, you do perfect spectrometry. And you cannot get the lines, but you don't need lines here. I mean, just maybe for dark matter, but otherwise you don't need lines. So it's perfect spectrometry. Angular resolution, well, it's fine. It's fine. It's 0.2 degrees is not so bad, especially if you have extended sources. Would be better to have better. And in that case, the Cherenkov telescope could replace. Of course, they cannot go. By the way, you just look the CTA sensitivity is Lhasa almost 1/2 order of magnitude worse than Lhasa. And so these optimistic predictions for CTA, for PeVatrons, it's a bit not exaggerated, but we have to be careful. And Lhasa just operates now at 100 TeV with such sensitivity. But you need CTA or other Cherenkov telescopes if you want to do better morphology, go to the details, because they have much better angular resolution. So in that sense, it's complementary. So, and this is a mega project realized in quite short time scales and working perfectly now almost without problems. And it consists two types of detectors. You go low energy part, it's just water Cherenkov detectors from 1 TeV or even less to 10–20 TeV. And these detectors also operate just now. and is 4 times larger than Hawk. And I should say also very good words about Hawk, because it was much modest, but this team succeeded to get a very nice results. So at the edge of what they could do. Of course, now this instrument, of course, is having such a large area, then there will be just much more, but Hawk historically did a very good job. Okay, so that was the first publication of this instrument. I mean, you see the location of these sources. Was chosen only 12 sources in the Nature paper half a year ago. And you could say, why 12? It could be, there are more, but there are extremely high standards to have more than 7 sigma above 100 TeV. Not all signal, just above 100 TeV should be more than 7 sigma to enter in this list. So that is really impressive. I call your attention to the energy, which is the first one is the Crab Nebula, and look the maximum energy, 0.88 PeV. But that was in the Nature paper. Later was another paper when now is 1.1 PeV. And look at this source 2032, its signals region, and you see it has been detected 1.54 PeV. And now, I mean, it was not the half instrument. Now instrument was completed fully since July, and the text, of course, continues. It's predictable, you know, the rate, and then if they're extended, there's no variability. You could predict what statistically will grow. So it goes like predicted, and it's more than impressive. I mean, you have tens of, not 100 events above 100 TeV. You imagine 100 events above 100 TeV just for a quite short period, and this instrument will operate another 10, 20 years. So now another, you could ask, which are the sources? Well, safely is identified only the Crab Nebula. Others, because they're extended, there are a lot of astronomical interesting objects surrounding. There are old supernova or middle-aged supernova remnants. You could not discard them. Supernova remnants cannot mid-age produce cosmic rays with energy PeV. But this we could see echo of the supernova remnants. If they have a nearby cloud, so supernova remnants left, they hit the cloud after 10,000 years, 100,000 years, and then we see now this echo. So these clouds are like smoking gas, just to identify, because we don't have many young supernova remnants at this moment. It's just, but this is a very nice way to detect them. Another thing I want to say, calling about PeVatrons, so there's no strong definition about the PeVatrons, but there are two things I want to, because there are a lot of now even conferences, talks about the PeVatrons, and they call all these sources PeVatrons. These are not PeVatrons, these are gamma ray emitters. Where is the PeVatron? PeVatrons means that where particles are accelerating. Could be inside, could be even outside, we don't know. But we still should find them and identify. So these are gamma ray emitters, so not PeVatrons. Second, what you call PeVatron? Again, I think we should not go and be so precise. I mean, 1 PeV or 1.1 or 0.9. These are PeVs, okay? But look, there are only 2 reliable mechanisms, or maybe 3 proton-proton interactions, inverse Compton, and maybe P gamma. So same P gamma, PP, in order to produce protons with energy, like gamma rays with energy E gamma, you multiply factor of 10. Typically 10% of energy goes to the gamma rays. However, if you have steep spectra, it's not 10. It could be 3 or 4. So in order to claim 1 PeV proton, you need 3-4 times more. So you need at least 300 TeV gamma rays for PP interactions. For inverse Compton, more or less the same. Inverse Compton is only on 2.7 K because there's a so-called Klein-Schiene effect. So could be density of optical radiation. You could go close to the stars to get more and more of the radiation, but because of Klein-Schiene effect, it's just suppressed. Anyway, so this is just these 2 things just to remember. If you have real PeVatron, you need a gamma ray energy about 300 TeV or more. And remember, these are not PeVatrons. These are just, again, you could call it smoking guns. I mean, producing gamma rays. So you still need to find the most exciting thing, these accelerators. So, and these will be accelerators, as I said, incredibly effective. But it's even not sufficient to is incredibly, because there'll be another one accelerators. These are electron PeVatrons, and you'll see they are electron PeVatrons. Then incredible doesn't characterize very well because they are extreme accelerators. And extreme means not just emotional characterization, extreme means absolute extreme. So just at the edge of the theory. And so these are all electron accelerators. PeVatrons are extreme accelerators, not proton PeVatrons. Proton PeVatrons are just, should be extremely effective accelerators, but extreme has a meaning. So meaning is this one. So in classical electrodynamics, the maximum rate you could get, you express the acceleration rate through electric field, but then you write the electric field in the terms of the magnetic field, like eta parameter, electric field to be. And then you have this, often in literature, you see EBC. This is wrong, by the way. Magnetic field doesn't accelerate particles. Electric field accelerates. So relation between electric field and magnetic fields. And this eta parameter, so this is classical electrodynamics. This is much you get. But then you could say, okay, I have an electric field larger than magnetic field. No, it's a classical MHD theory. It never happens that electric field is more than magnetic field. So there could be some situation you could, okay, you could have capacity condensator, could say you have the drop of the potential, but in reality, it's very difficult to get electric field more. Now, in order now to get electron PeVatrons, this eta should be very close to 1. That was called extreme accelerators. So that's what I want to say. And this is a very interesting feature of these accelerators because they emit synchrone emission, and it appears that synchrone emission, you see this beautiful formula. I mean, eta minus 1 mc squared over alpha. Alpha is the fine structure. I mean, okay, it is maybe unusual to see fine structure, but it's a combination of different parameters. And that for electrons is a peak is about 100 MeV or 150 MeV or 0.15 GeV. And for protons, it depends only on the mass. For proton synchrone, it goes to 0.3 TeV. So this is the specific feature of these extreme accelerators. If you detect them, and it seems Crab detects this, you heard about the Crab flares. So that is exactly that number, 150. And in fact, they are surprised that it goes even beyond that. So necessary to understand what could be the reason of that. Okay, that was what I was saying about the Crab. You see the synchrone peak is about 10 MeV and then goes to up to 100 MeV, even more. So you could say is extreme. Now, what is it, 0.1 or 1? Difficult to say, because also you could say what is the maximum frequency, the maximum energy of synchrone photons. You mean the maximum of the cutoff energy is maximum, but could be continued. It's not very clear. So it's to determine how is effective this accelerator. But if you accelerate particles, you get gamma rays with 1 PeV energy. You could immediately calculate the energy of the electrons. It should be 1 PeV gamma ray gives you 2.5 PeV electron. And you see the absolute maximum is 6. Sorry, it should be PeV, again, another typo. So Emax is 6 PeV for 100 microgauss. So magnetic field cannot be much less than 100 microgauss in the Crab. So you are very, very close in the Crab. So, but this is now model independent. You don't do any speculation where they are accelerated. You just, this is unique in astrophysics, by the way, 2.7 K upscattering, because you know your target, you know cross-section of inverse content. So you immediately get your energy of the electron. And you see this is a unbelievably large energy. And now we before had a 10 TeV, it was large, okay. And then was 100 TeV, and then Lahasso arrived and detects now PV photons. So, so this is an extreme accelerator. Now, okay, let me skip about 10 to 20 because it's another thing, but just to mention, another case of the extreme accelerators are accelerators 10 to 20 photons. So this comes from the very simple, famous plot which did Hillers many years ago. It looks like something simple-minded, naive plot, but it has a lot of implications. It's very deep, in fact. And then if you put on this plot known object, you could say, okay, there are only few in the universe which we know could accelerate 10 to 20. Some of them are clusters of galaxies, AGN, maybe GRBs. But if you go details, you could just reject the clusters of galaxies or remain AGN. So, but let me just stop at this, not to go to detail, but I say this is the second example for extreme accelerators. So one, electron PeVatrons are extreme accelerators, and 10 to 20. Maybe there are some others, but these two for sure. Now galactic cosmic rays. So we know I said they are the mystery, but you know we know so much about cosmic rays. In fact, so we detect primary, we detect secondaries, and actually we should be carefully calling positron secondaries because partial accelerate also positrons, but also you detect secondary nuclei like beryllium, lithium, which should not be as much as we detect. And then you could immediately say how much matter they should propagate to produce this ratio, secondary to primary. So it's called grammage. And having this grammage, you could estimate the confinement time of the primaries. Knowing the confinement time, you could derive so-called diffusion coefficient. And that has this form, I mean, this like power law form. And this delta could be 0.3, could be 0.5, depends on the turbulent mode. Like 0.3 is a favorable one for Kolmogorov turbulence, but could be 0.5. And the extreme one is called bond diffusion when this delta is 1. So in interstellar medium, this delta you measure from measurements, just this is not it's a measurement, it's about 0.5, 0.5, 0.6. Now, why is that important? Because what we measure cosmic ray spectrum, they are modified. We don't see the source spectrum. We measure modified one. And in that case, we should correct, if we want to know what is the source spectrum, we should correct for this delta parameter. And in that way, we get it. Now, so basic facts, you know, they are written here. As I said, this delta, the diffusion coefficient is assumed to be 10 to 20 at 1 GeV, and dependence 0.3, 0.5 for delta index. And the production rate is about something between 0.3, 1 times 10 to 41 arc per second. And the source spectrum look should be then, we detect gamma 2.7, 2.8, it is measurements. Delta 0.3, 0.5, so alpha source spectrum should be close to 2.3. Now, just as I mentioned, 10 to 41 per second, that was an amazing thing that in 30s, 33, 34, Baden-Zwicky wrote a paper and predicted that supernova explosion, they called supernova explosion at that time, that could be responsible for cosmic rays. It was amazing because they correctly estimated the rate of production of cosmic rays. And then they said, okay, you need 10 to 41 arc, supernova explosion is given 10 to 42. If 10% could be converted, then it could provide. So energetically, it was idea. Later appeared diffusion, so-called diffusive shock acceleration theory, which is a kind of sophisticated way, is a Fermi mechanism. So what suggests Fermi, but in some way you could call that. And that was very successful. And so there everyone was just happy. So energetically it's fine. And then, but you need to prove this concept that supernova remnants are the major contribution to cosmic rays. Gamma rays, I said, is the best. with the gamma rays, and then you see now the spectrum. One is gamma rays, 1,000, 2,000-year-old supernova remnant. It's not classical supernova remnant, but it was found. And you look the image. That is the gamma ray image, by the way. This is not X-ray image. I just mentioned that often because I remember when I was reporting the result, it was a COSPAR meeting, 2004. It was the first time we announced detection. And I showed that it was very short talk, some 10 minutes. And at the end, no one realized that I was talking about gamma ray image. They are thinking I'm showing X-ray image, talking about the source, and they are just kind of shocked that they are showing gamma ray image. So that was this image. You see the spectrum, and then you could derive either proton spectrum or electron spectrum, depending if hadronic, leptonic. Looks very nice, but there was one disappointing point. The spectrum, proton spectrum, let's assume, let's not discuss the leptonic or hadronic, let's assume protons. And then you see the cutoff at 100 TeV. You would like to see TeV. And then it was a kind of disappointment, which should not be, but nevertheless, again, there are a lot of details. But what disappointments arrived even more later, because there are a lot of gamma rays have been detected from a lot of supernova remnants. These are young supernova remnants. They are about 2,000-3,000-year-old supernova remnants with shock speed few thousand kilometers per second. That is absolutely necessary to get that. Everything is again, you are happy with images, you see beautiful shells, or kind of shells, but spectra were very steep. Was 2.4, 2.5. It could be how you get the steep spectrum. You could get a flat spectrum and put exponential cutoff. So combination gives you some interval power law. So necessary to be very careful with this formal mathematical definition, because you could get any cutoff, and you could fit also E-1, like cutoff at 1 TeV, E-2, cutoff 10 TeV. So it's just presentation. So it could be 2 times. So you have a hard spectrum, but then you need the early cutoff earlier just to get the steep part. Or it is steep. So this is very interesting point, because a lot of people are unhappy with steep spectra, which is because they have in mind diffusion shock acceleration E- beautiful spectrum. But that is really strange, because E-2 doesn't match cosmic rays. It should be E-2.3, 2.4. So, and then if you go deeper, there's a lot of activity of recent years. In fact, this is ideal picture of diffusion shock acceleration with E-2 is not the case. You get steep spectra. Now, question is, the spectra continues to PV or not? This second question. But if it's early cutoff, if it's, that was I mentioned, there could be, if this is early cutoff, it should be 10 TeV on the 100 TeV. So then, yes, then it's not a PeVatron. But for steep, you could not say that. It's not, it doesn't contradict anything. So you need to go, what is the idea? I mean, if you do steep spectrum in 1 decade, you never get, it's very difficult to measure. You need a distance to measure it. So you have to continue and continue above 100 TeV. And that is says that all your unhappiness is not justified, because simply the existing detectors could not detect 100 TeV. So I showed you archive this typical supernova remnant, Casey, 300 years old. And you see, if you extrapolate spectrum to 100 PV, which is the important point to see, it could work for PeVatron or not. Look at the sensitivity at the flux is expected, 10⁻14, and look sensitivity. I'm not talking about Hess or Magic or others, just CTA. CTA cannot also do that. I'm so surprised to see all this very often claiming it will detect. Yes, they'll detect, but not 100 TeV. But we are lucky that, look, the Lhasa can do that. But even for Lhasa, after 5 years. And that is very important. But you know that Lhasa answer to your question. There's 100 people, and that is only after that you could say is a PeVatron or not. Now, there's one trick here. If I don't detect, you could always say that theory actually favors that. So we are thinking before supernova REMS actually particles in the so-called CIDR phase, but it could be just accelerating much earlier. We're talking about 100 years, now it could go even few years, so there's also theories. And then you say, okay, observers, you are hopeless to do anything. Whatever you don't get, I'll say it happened and you don't see that. It's not the case. You could not trick because this is 300-year-old supernova remnant. So if they go rectilinearly, they'll fill about 100 parsec region maximum. They could not go, so they don't escape this area. And Lhasa will also observe this part. It will be in the field of view. Lhasa is 1-2 degrees. Unfortunately, the density is quite high. Kasei is well known. Is within the dense area about 10 per cubic centimeter density. So you could put very strict upper limit. And after upper limit, you could answer to the question, it is PeVatron or not. If it's not PeVatron, you could say it never was PeVatron. So that is a very important thing, which is just when you tell some people, I mean, your Lhasa, they think, well, his upper limit is not exciting. But this could be upper limit, in my view, cost tens of other detections. So now, let me just move to another thing I already mentioned briefly, that it could be, so we have only a couple of, not many historical young supernova remnants. In Northern Hemisphere is only Tycho and Kasei. In South, say 2006, so not many. So you could not even conclude on basis of one circuit. Kasei was a kind of unfortunate source. But there are much more middle-age supernova remnants, like 10,000, 100,000 year old. And you no hope to detect any gamma rays from these objects. But as I said, you could get a smoking gas nearby clouds. And we well know there are a lot of sources are close to this. So in that way, you could get information about these sources. And so some of them is the Lhasa sources. This is one, which one is 1908. There's a supernova remnant, middle-age supernova remnant. So that could be the case. We should go that. Yeah. Okay, so now, now I'm going to talk about, because this is a cosmic rays, I'll skip the electron part. As I said, already said a lot about them, but the cosmic rays are interesting. So let's assume we don't detect Kasei. So what will be next? And now we have mounting evidence that young stellar clusters emit better gamma rays to highest energies and even right spectrum 2.3, and a lot of energetic is there. Actually, this idea comes from some 40 years ago by Larry Czesalski, that young stellar clusters could be good sources as an alternative to supernova remnants. And now we do see there are good arguments. But what is important, we see gamma rays from them. Moreover, we don't only see gamma rays from them, but we see features of this object, because the clusters, so I call that the young stars versus dead stars. I mean, dead stars are supernova remnant, and these are young stars. They operate already a million years. It's continuous injection. In that case, you see distribution of the protons like 1/r. And that is derived from gamma ray data is close to 1/r. On the spectrum, you see there are different types of these clusters. One of the signals using the Argo source was the maximum one we used here. And that was also very close to 0.2 gamma ray spectrum, proton spectrum could be 2.3. And now I mentioned the Hawk. Hawk recently reported that gamma ray from Cygnus region goes to 100 TeV. By the way, Hess started to also measure up to 100 TeV. Hess cannot do anything beyond 100 TeV, but for Westerlund 1 is a very special stellar clusters, it goes to 100 TeV. So Hawk did that. 100 TeV is nice, but the LHAASO now found 1.4 TeV gamma rays. So no one could even dream to have 1.4 TeV, but there's the case. So these guys are clear. These are protons, and they emit. So in order to get this energy of the gamma rays, you need at least 10 PeV protons. So that is the clear. And now this was published, no spectrum, just at one point. Now LHAASO accumulating data. I mean, unfortunately, these are not public available. I cannot tell about that, but they're extremely exciting. And the statistic I can tell you because you could calculate yourself if you are going there. And that is a tens of TeV gamma rays above 300 TeV. 300 TeV, just it is a background free. So this is going to be a real big breakthrough. And so since I have only 5 minutes, no anymore 5 minutes. I think it's last 2 minutes. Okay, I just say another interesting point is just super PeVatrons. Maybe you could ask these questions, what are super PeVatrons, but at this moment, let's skip that. I just want to tell you about very exciting thing. Yeah, I mentioned just using that. So getting, I mentioned the gamma rays. Neutrinos will be difficult to detect because sensitivities, but you could detect X-rays from synchrotron radiation of secondary electrons. They are produced parallel to neutrinos, and they are cooled immediately. So we could say prompt X-rays and neutrinos, but X-ray there are no good detectors for extended sources. Now we have Rosetta. So Rosetta could be very nice complementary to these objects for LHAASO. Also, resolution of Rosetta is 10 arcseconds. Only the problem is there are other X-ray, so could we reveal that or not? A last point I want to mention is the following. These are electrons. This is really not real part of this talk. I mean, I just put that just in case, because I already mentioned this extreme accelerator. They are Crab nebula and possibly nebula. Electrons are coming in range also 1 TeV, several hundred TeV. That I told you that is not simply incredible. It's just almost impossible, but we see that. But now coming back for the PeVatrons, there's one nice thing. I mentioned that you see the emission. You don't see emitter. You don't see the PeVatron. How you find the PeVatron? I mean, because PeVatron particles go, they're quantized, they energize the system, you see that. There's very interesting feature. It's almost model independent, only one thing. Diffusion should not be much slower close to this object than interstellar medium. Like even order of magnitude slow is okay. It is, in this case, particles, significant part propagate in ballistic regime. They are not quantized, they're isotropized. So it's called ballistic and then transition to diffusion. So significant part, they go like ballistic. And then what happened ballistic? You say, I don't care, ballistic, not ballistic. They just go and fill more and more space. And what do you expect? You expect more angular size, right? You're producing in 100 parsecs, at 1 kiloparsec, it's 2 degrees. It's not the case if they're going ballistically. Then, even they are produced in a huge volume, you see the very compact object. It's just shown here. So this is no real physics when I compare like superluminal in jets, but this is something like that. You see the image is a fake image. You think that everything is coming from the compact object, but in fact they are produced in a huge area. So what is the nice here? Okay, this is nice effect, physics is very nice, but it's more than that because implication. So these highest energy particles like gamma rays with energy more than 100 TeV or TeV, the image is projected on the accelerator. So if you see inside the diffuse source, like point-like source at highest energies, so increasing energy, effect is stronger. It will become smaller and smaller image. You could just localize the PeVatron. So that was actually what trying to do in Lhasa. So that is very specific aspect of this PV gamma ray extended sources. And I think we see that also for the electronic PeVatrons. But so let's stop on that. So just show the summary. Yeah, just okay, one more minute. I just want to say how interesting this effect. You see, this is the low energy for specific diffusion coefficient, 10 GeV, 100 GeV, and 1 TeV. So you expect increase of the angular size because they are propagating more. But in fact, you see the decrease of the size. So and we use that for clarions, and that could be very interesting debates about is diffusion or the size is another question. Just to summarize here is simple that the detection of the electron, I emphasize on proton PeVatrons by Lhasa, directly demonstrate that these objects are present in the Milky Way. The first real, you could say, you remember I started saying no way to have 10 to 15 1 PV particle for extragalactic, but still is a model. I mean, let's say magnetic field is extremely small, maybe they could still come. But here is just detection implies that these are PeVatrons in the Milky Way. Second, are these galactic or these PeVatrons, galactic PeVatrons, supernova remnants or young massive clusters? I did have mentioned to galactic center. That could be also another interesting object. Sagittarius A star in the center of the galaxy. So all of them, that is also possible. So this observation in Lhasa, I mentioned Rosita, and I told that CTA is not as perfect for detecting PeVatrons, but for strong one, it can. And it will be added value because beta angular resolution. And probably Rosita can do that. And the electron PeVatrons was not a part of this talk. I said these are just simply extreme accelerators and realized in our galaxy in the form of the passive nebulae. And the last point, I was very fast. Personally, I'm very excited this possibility that at PV energies, because we could not dream before to have these energies. As I said, we have tens of 100 TeV gamma rays or maybe hundreds in future. So, and if this effect works, that we uniquely, you could localize the accelerators in these objects. So that is all.
Felix, am I allowed to make a comment?
Yes, please. If there are questions.
This is Bruno Coppi, we are all friends. Introducing the parameter eta, as you said, makes sense if you do not have reconnection. Now, if you have PV electrons, a reconnection process become much easier, for example, than in space physics. So I think we have a new possibility to explain the generation of these gamma rays.
I am happy if you could explain. I am not so optimistic. Reconnection, of course, is the alternative and probably better alternative to shock waves. And I mean, the diffusion shock acceleration, sorry. And because reconnection was connected with shock waves. But if you can do that, congratulations. But I think it will take time. It's not so easy. I know that, for example, I mean, there are a lot of simulations, for example, by Sironi, Spitkovsky. And I talked to Sironi a lot about that because they do these peak simulations. They do get electron field, these islands of electron field, but these are not very stable. I mean, that they disappear quickly. But if you can do that, so fine. It's not contradiction what I'm saying. Then you could say, okay.
No, it's not contradicting. But
no, I just say this is a reconnection can explain. But yeah, it could be good motivation that to demonstrate that in reconnection, you could have electric field stable or quasi-stable more than magnetic field. Then I say congratulations.
Okay, yes. This is a question for Tonino.
I have one comment and several questions, so I will select the questions. So we will discuss the questions.
Just speak loudly.
The comment,
so that they can speak loudly.
yeah, the comment is related to the plot where you show the sensitivity of lasso. you show together with the sensitivity of another experiment that does not exist yet, that is the CT8 sound. So it is, we really cannot appreciate the sensitivity of laser in the full energy range, because CTA sound, when will be discussed, will be better than last. But now the only experiment existing is last.
But even more, because I mentioned that even CTA will happen in the best way as planned, still at 100 TV.
No, but was a comment for this block.
Yeah.
My question, I selected one question out of the several questions that they have. You said, pay attention, this is the place where the photons are produced, is not the PeVatron. Now, even if I have a PeVatron, if in order to produce this gamma, I need some target where I can make the interaction between protons and whatever it is, and this matter, or radiation. But this cannot be so far from the accelerator. So anyway, the place where photons are coming is the indication of the position of the PeVatron.
Not really, for the following reason. If you, first of all, I mean, okay, let's have more astronomical, very broader, right? So typically these are accelerators, the PeVatron, these are fresh ones. So they are connected to the star-forming regions. Star-forming regions are full of molecular gas, because that actually gas produces the stars. So it's very interesting. So gas produces stars are accelerating particles. So always you have this giant molecular clouds. This is one. So, and inside the source actually should not be much gas density, because you could reduce it, not a vacuum, but better to have a low density.
So you said it's a low density.
Yeah, because like they called like effect like Landau damping, there are other effects. So they have low density inside accelerator. And if you go now specifically use supernova remnants, of course, there's not much gas inside. I mean, we know one or two in Casset, so it's not huge. But the cloud is just the dump cloud is nearby. They don't know about your accelerator, just sitting there, and they are dense. Could be 10 to 3, 10 to 4 per cubics. And then another option is just if you have the compact accelerator, particles escape so quickly, so they don't accumulate the grammage, let's say, in that language. So, by the way, you could add that Silvia, we wrote a paper with Magic for this gamma Cygni, and they also considered that both escape and hitting the cloud, and you could see there this interesting, actually we had even here, I don't know if to find it easily or not. Yeah, this thing actually comes from Stefano Gabic, and we wrote in 2007, we just used how to detect PeVatrons, neutrinos and gamma rays. And you see that that is the supernova remnant at the beginning, how much in its supernova, it's typical parameters. And you see it goes to the one is 400 years formally. But then if you go 2,000 years, 8,000 years, you drop, because there are no particles, they escape. And then you put the cloud at some, I think it was 100 parsec, you put a cloud, and then at the beginning you don't have anything because particles need time to come to the cloud. But then with time, they are approaching us. And as you can see, for example, for 8,000 years, they just tick there. And then the cloud has density 10 to 3, 10 to 4 per cubic centimeter, opposite to 1. So that could be, and that was, I mentioned gamma Cygni, there was even more based on observations. I mean, that was, so clouds are better. I mean, if you put the cloud in the accelerator, you'll kill your accelerator. You'll be no any more acceleration there. So
I think there was another question, maybe from Aldo. Yes, please.
Yes. So you mentioned that Erosita can help in this game. What about an instrument in the MEV region, so the region below the Fermi energies?
It'll be better. It'll be better, not for PeVatrons. PeVatrons X-ray are better because it's X-ray band. I mean, I think I had somewhere where it was. I mean, it was. Yeah, so this is our paper with silver, by the way. So it is just we have cut off at 1 PV, you see the X-ray band. But what you are asking is extremely important. So actually we are going to write the paper on that. So that was, so to go to super PeVatron, so 10 to 100 PV, then maximum comes to MEV region. So you need MEV instrument, MEV or 10 MEV or 100 MEV. You see exactly the MEV, second electrons in MEV band. So, but this for super PeVatrons, which could be actually even more exciting. But for PeVatrons, it's just typically it's of course the magnetic field you could increase, but even order of magnitude still will be in X-ray band. On the other hand, the erosivity is good because of angular resolution. You never get 10 arc second with MEV, but yes, I mean that would be great to have MEV for this purpose.
I think there is one last question from home. It was Daniele Farjon, so please.
Could you hear me?
Yes, we can.
Hi, Felix. I wish to make a small remark. There is the shadow of the moon and the shadow of the sun, which are important tool to verify the system of LASO. Now, the same shadow of the sun may contain skimming ultra-high cosmic rays at PVs, which produce muons. Those muons may decay in flight, producing electrons at 100 TeV, and that could be, in principle, able to be observed from the same LASO, both inside the shadow of the moon and outside. I think it could be a remarkable discovery of cosmic ray skimming the atmosphere of the sun. I hope you can give a look on this argument, which was proposed a few years ago by our group, and Klopov is inside the group. Let me know.
Yeah, okay. I start to remember that. I mean, yes, I could pass that to LASO. They observed the sun and moon because calibration. So that is interesting point. And if you could even write like Tensao, also could write to Pino. Pino is also in this kind of things involved. So, and then he could discuss with the collaboration, LASO collaboration, and then, yeah, it's very, very good point. I mean, because it's, you know, before you are suggesting different, I mean, for Cherenkov, it's always difficult to push to observe something or some ideas, but this is for free. I mean, all data are there. So all these possibilities should be explored. I agree with you, just as and that could be done. I mean, I think the best you write a Pino and you could contact them and then.
It has been done. Pino invited in a conference with China's, and I think I made the first sentence.
Yeah, but if you don't have data, if you don't have data, these are only ideas. Now there are data, so it's completely different situation. No one has to remember, you know, that was, this is a thing, there are so many things to remember. But if you have now fully agreed that you just suggest them, it's not too late, it's just they start to analyze. So no problem.
Okay, so
thank you. Thank you.
Last comment, right?
Yeah.
Okay.
So if the chairwoman knows me. So I'm curious also because I'm ignorant, because it is important for the paper that we have written. You say that if we see X-rays from a source like that, this is a clear indication that the source is hadronic. Actually, this would be very interesting because we have been studying the chocolate GLBs from which you don't see gammas. if really we have to expect the production of X-rays from these GRBs, we have at least a tool to try to identify these sources.
That is up
But
to,
why it is only in hadronic and not if the source is leptonic?
okay, that's what I want to say. So here the problem only was with thermal. So there are a lot of other mechanisms for X-ray. So first so actually, if you took it very formally, it's there better even neutrinos in the sense sensitivity. But neutrino, you have neutrino, you don't, the X-ray, you still should prove that these are for the same channel, for this channel. So that is the biggest problem. So for primary electrons, that is a bit easier. 6 from primary electron, because 6 from primary electrons depends on the, let's say, supernova random shock speed. So it's around 1 keV, then goes down. And this could go, because in order to observe the electrons, magnetic field is some interesting ways working, so it does depend on magnetic field. Here, you observe particles too high energies. So you could observe with supernova rain more than 100 keV, because energy losses, neutron losses. But here you do trick. You observe protons, it goes even much more, and then you get electron, and then they could produce. So, and that will harder spectra, but it will be a lot of problem. I mean, not so easy to identify them as for this method.
So the answer is because the electron have higher energy. In the hadron case, with the electron.
No, hadron, yes, much higher could go, but there are some other electron producing mechanisms, so you still need to prove that is the case.
That's interesting.
But I think an interesting clue could be, the normalization of the gamma rays, from pi-0 decay with respect to
Sure, no, of course
the
you have
secondary
to combine, but you see
X-rays,
it depends
yes.
on the spectral shape.
Yes, it depends
So-
on the spectral shape.
So
Yeah.
that was
Yes.
this is your plot. So
But in principle, if they come from the same protons, yeah, you know the contact.
it's hard work.
Yeah.
But it to be very interesting. And that would be not impossible before, because X-rays are small field of view instruments like Chandra, XMM. Here you have a Rosetta, but still the Rosetta sensitivity is less than Lhasa sensitivity. The Rosetta sensitivity for at the end of 4 years will be 10 minus 13 of square centimeter per second. And Lhasa is 10 minus 14. And what says that was another point you said about MEV. Could you get MEV 10 minus 12? Difficult. Yeah, try. So I just want to say that what reached the Lhasa? I mean, that was interesting just to compare these numbers. I mean, and that would be not interesting if would be no PeVatrons. But if there are so, there are sensitivity. So that is interesting aspect of Lhasa.
So bright results to come.
Yeah, for sure. It is there. Actually, they are coming. They are there. Much brighter result than
We are
now.
waiting the publications.
Yeah.
And unfortunately, it depends from ESA, because it's not approved the experiment, then we will not have.
Yeah, I saw there's my friend Bruno Coppi was there.
Yes,
I just sent him.
Okay, so.
So let's thank again Felix. And we can close the call. So thank you